Hi, I'm Joe Soja of Cadence Design Systems. Welcome to Sigrity Tech Tips. Today we bring you another installment of how to sign off using a power-aware signal integrity methodology. Our video today will show you how PCB designers can improve the screening stage of your PCB design flow using power-aware rule checks. Traditionally, printed circuit boards go through a pre-route analysis and floor planning stage before the design is routed, and then both a screening and a post-route detailed analysis. The screening stage is meant to catch glaring problems that used to be limited to geometrical rules such as length and spacing checks. Eventually, electrical rules such as impedance and crosstalk were added to this screening portion of the PCB design flow. With today's complex designs, establishing confidence before building a prototype is becoming a greater challenge. Screening has its limitations, and to perform detailed simulation on a full design is likely too time-consuming. To address this challenge, designers have been seeking improved electrical rules so they can continue to have high confidence before building prototypes. Electrical rules have been limited to checks that assume that power and ground rails are perfectly stable, but this is not true in the real world. A number of designs have passed these electrical rule checks, but still failed either in the factory or in the field because of the hidden problems caused by power noise interfering with signals, causing loss of revenue and market share. But now, with the power-aware rule checks available in Sigrity technology, PCBs can be more effectively screened by the PCB designers. Combine this with power-aware detailed simulation, and once again, design teams can have high confidence that their designs will not only work in the lab, but will also work long-term in the field. The result may likely be higher profits, higher market share, and even higher stock prices. In today's video, you will see us utilize the Allegro Sigrity SI base and power-aware SI option. To learn more about these products, visit us at www.cadence.com. Now I will turn it over to my colleague, Jen Mu.
Thanks, Joe. In this video, we will discuss first the meaning of sign-off, the issues with physical rule-only flow, and the unique solution provided by Cadence Sigrity tools. What does sign-off mean to a high-speed PCB designer? From the computer-aided design point of view, many people would answer the question as the completion of design and verification in the software environment and ready to release for building hardware and testing. Here is an illustration of typical sign-off flow. You can see that in the different design stages, SI-PI simulation first help extract and set up design constraints. After the constraints are implemented on the board, rules for physical layout and routing will be examined to see if all the constraints are correctly done on board. Any violations to the constraints has to be evaluated and investigated using SI or PI simulation. The result of this simulation will guide design modification. Such iteration goes on until no SI or PI EMI issues, which to many designers and even for many tools means that the design cycle is finished. In other words, the design is signed off for hardware realization. The question here is, does this type of flow satisfy today's high-speed design requirements? Or can this type of flow identify or correct all possible design issues and give high confidence to designers about the success of their product? Let's go back a little to see how the sign-off flow we just discussed is evolved. The flow is basically constraint-driven, without integration with layout environment. It originated from the first industry constraint-driven flow, that is the Allegro constraint-driven flow, which was introduced to designers in 1995. The constraint-driven flow first contained only rules to prevent problems with SI and EMI. Over the past 20 years, as technology advances, signal rate goes up and the power supply level goes down, and the new simulation methodologies introduced like PI analysis, SerDes analysis, and high-speed memory bus simulations. More rules are introduced. For example, decoupling capacitor displacement rules for PI application and differential signal rules for serial link designs. With smaller noise margin on signal and power supply, designs today require simulation result of signal and power iterations. The new simulation technology is supported by power-aware IBIS modeling, signal power extraction, and return path handling. On rule checking side, however, there is really no rules set up yet. If we examine the sample sign-off flow again, we can see that there is no checking on power noise effect on signals. In other words, SI and PI problems are still checked out separately. More importantly, all the rules are still physical layout check based, and the same assumption for constraint extraction and the rule check is used. In other words, constraints are at the pre-layout stage are set by assuming ideal reference planes, while rules are checked at the post-route stage also assume ideal reference planes. It totally ignores the power noise impact on signals at the post-route stage. So this flow is not complete regarding identifying some serious potential design issues. PCBs signed off with this type of flow will have feed-in problems with signal degradation caused by power noise. The worst of all, designers don't even know it. Now the question is, how do we make the sign-off flow valid again by including identifying power noise introduced problems? First, we need to understand that power noise couples to the signals and will change all classic SI problems, such as reflection, crosstalk, and timing. Then, of course, SSN and power supply switching are typical. The next question is there any rule available to check the power-induced problems in a design? The answer is no. It's because the plain noise impact on signals is difficult to model, and it may not be easy to get any simplified formula to derive rules for practical use. Then, how do we check the problems? From previous discussion, we can see that our only option is to go with simulation and modeling on power and signals. But performing SSN type of simulation in post-route environment with nonlinear models requires special field solver to handle power planes and shapes, therefore have performance issues. This cannot be used with checking purposes. Designers need fast checking tools to quickly obtain potential design issues. Do we have a tool for power-aware design checking? The answer is yes. Cadence Sigrity provides SI matrix check for the complete power-aware solution. It can check and report general classic SI issues and for power noise-induced SI problems. Now, let's take a look at how the quick checking tool works in Sigrity's tool environment. As other Sigrity's tools, SI matrix checking has a workflow for user to follow the process of setup, simulation, and result reporting. After reading in a design, we can select signals with similar behavior, such as data signals in DDR design, to form a net group. Eventually, the result of the same group will be reported together, easy for user to compare. Then, we can set up the linear excitation to each group with also termination conditions. Later, we can decide how to run the simulation. As we have mentioned earlier, We can set it up for a classic SI type of check by assuming ideal power delivery network, or we can set up for power-aware checking using the built-in hardware hybrid solver. We can even select 3D field solver for certain signal nets if necessary. When simulation is done, waveforms of signals and the near-end and far-end crosstalk are displayed for each signal at every pin. Then we can generate a report for the waveforms with measurement and sort out signals by the overall quality. The signal noise ratio and other parameters are all calculated with either ideal PDN or non-ideal PDN with hybrid solver, or even 3D solver as we selected before simulation. You can see designers can judge the overall signal quality based on the report and select some of the signal with high signal noise ratio to run more detailed analysis. One significant benefit of using SI matrix check is to pick up crosstalk impact through plane canvas or between signal vias. For example, when higher crosstalk is observed on a signal in simulation without power noise, we can increase the distance separation to reduce it. With non-ideal power effect, this may not be true because of the extra crosstalk from signal via coupling through plane canvas or plane bouncing. The remaining question now is if the constraint-driven flow still will be valid. What should the designers do with the checking result from SI matrix? We should remember the goal of any design checking is to use other, more detailed simulation tools to evaluate the severity of the problem found and for designers to decide if any modification is needed. With the power-aware checking, the goal is the same. The report of a SI matrix sorts out the signals with bad performance so that designers can run detailed simulation with non-ideal power supply. Then examine existing decoupling capacitor placement and selection schemes to make plane quiet. In other words, to make it close to ideal power. When that is reached, the constraint-driven flow becomes complete and sign-off is achieved. Here is the new design and verification flow with power-aware capability. In summary, constraint-driven flow needs to advance to a new level to account for power-induced noise on signals. Designers should check their current sign-off flow and update it with power-aware functions. Cadence Sigrity tool can help to achieve that goal.
Thank you for watching another edition of Sigrity Tech Tips. For information on products used in today's video, click on the links below or contact your local Cadence sales representative or Cadence channel partner.